The next part of section 1 is going to discuss the idea of set operations. So previously in part 1, we discussed the notion of what a set was, and we discussed it in a finite setting as well as a infinite setting. Now, when you're dealing with just a single real number, you are familiar with the idea of operations. So for example, what you've encountered in your life are things called binary operations. So for example, if I was to give you the real number 5 and the real number 3, there would be 4 different operations that you could do with these two real numbers. You could add, you could subtract, you could multiply, or you could divide. Now the idea here is that you have to have 2 elements in order to be able to do that with. Now our elements here are just real numbers. So when we take these 2 real numbers, we perform the operation of addition, the result is still a real number. But it's a real number that's different from either of the 2 that we started with. So it's taking 2 of one type of object and turning it into another of that type of object. So the sets that we've been talking about in this section also have the ability to have operations applied to them. So in order to do this, I have to have more than one set. So for definition purposes, we stick with 2 sets. If I have a set A and a set B, there's an operation called the union. And the union is represented by this symbol right here. It's this sort of looks like an uppercase U, and the purpose of that is to be the operation symbol. Now that operation symbol is defined to be a compound statement. We discussed compound statements in an earlier example, and this is an OR compound statement. So that means that the union only requires that one of these 2 statements be true in order for an element to be a member of the union. So what this really means from a Venn diagram perspective, which is what we have here, if this big circle right here represents set A, and let me pick out a different color, let's go green, this set represents set B, then the union, that's what this is saying right here, union of the 2 sets, is when I take all of the elements from A, all of the elements from A, and all of the elements from B, and I just put them together into one big set. That's what a union does. Now, another operation that we can apply is known as the intersection. Again, in order for an intersection to take place, you have to have 2 sets. So in this case, for definition purposes, we call them set A and set B, but in general they could be named whatever. And the symbol for this is what looks like the upside down U. It is also defined by using a compound statement. The compound statement is an AND compound statement. So that means that both of these statements have to be true in order for an element to be a member of the intersection. So from a Venn diagram perspective, if I have set A right here, set B is here, then everything here is in set A and everything here is in set B. But the part that's in the middle is the elements that belong in both A and in B. Because it's certainly conceivable that a set could have the same thing in it as another set. How there's only so many real numbers, and sometimes those real numbers get reused. So the intersection represents the overlap of the sets. So I oftentimes think of the intersection as being elements shared in common. So any elements that are shared in common would be considered part of the intersection. Now, something else that is conceivable is that two sets would not have anything in common. So in the event that two sets do not have anything in common, we have a way of discussing that. That's what definition 1.5 says. It says the set that has no elements is called the empty set. So anytime you encounter this, you certainly can write out the English words empty set. But mathematicians are known for having symbols for a lot of things. So this is no exception. We have a symbol, which is this 0 with a slash through it. This represents the idea of empty set.